All right, welcome to the first KCS talk of this semester. Our first talk will be given by Lasantha, okay, on this topic here. Causal necessity as a narrative planning step cost function. The speaker will show that prioritizing sequences with more causally necessary actions can lead to solutions faster in 10 benchmark uh, story planning problems, such as the deer hunter problem, the secret agent problem, the hospital problem, the space problem, the fantasy problem, the western problem, the raiders problem, the grammar problem, the jailbreak problem, or the lovers problem. Okay, so let's welcome Lasantha for his talk for the first KCX talk for this semester.
Yeah. Thank. Okay. Thank you. Thank you, Professor Cheng, for giving me the chance. So, my name is Lasantha Senanayake, and I'm representing Narrative Intelligence Lab. And in our lab, we investigate how computers can use narrative to interact more naturally with people. So we combine research in artificial intelligence, narrative theory, and cognitive science to create computational models of narrative. So I'm presenting today Casey's talk, and this is the title. The title is Causal necessity as a narrative planning step cost function, and we, Dr. Stephen Weah and Rachel Farrell is we conducted this in Narrative Intelligence Lab. So we presented this paper in 19th AAAI conference on artificial intelligence and active digital media entertainment, or known as AID. So we conducted our research using Sabre, which is a free and open source product of our lab. So I'm going to give you a little background on Sabre. So Sabre is a narrative planner, and it is a centralized decision maker that solves multi-agent problem, multi-agent storytelling problems. So Sabre can categorize as a forward state space planning algorithm that generate a sequence of actions to improve author-defined utility function. So in Sabre, every time an agent does an action, that agent needs to believe the action leads to an improvement in their utility in a storytelling problem. So as I told you earlier, Sabre is a forward state space planning algorithm. So the search for a solution begins in an initial state and follows edges forward until it reaches an acceptable terminal state where the author goal is achieved. But every action taken by an agent or character to come to this terminal state must make sense according to that agent's individual intentions and limited, maybe possibly wrong beliefs. So each of these arrows are actions, and you can see the state after taking that action in those gray circles. So according to these constraints, Sabre gives us a solution. So a solution in Sabre is a sequence of actions which can be executed and leads to a state where author utility is improved. So here, each and every action taken by a character, that character needs to believe that the action can lead to increase of their utility. So we have 14 problems that we use to benchmark Sabre, and here is a list of them. We run Sabre algorithm on these problems, and we get plans or sequence of actions, as I showed you earlier, out of these benchmark problems. For simplicity, and to give you some examples, I'm going to use the grandma problem, which we always use in our presentations, so I'm going to stick to that. In this grandma story, there's a cottage, and there is our Tom, who lives in the cottage with his grandmother, and she's sick, and Tom needs to heal her. Tom does not have potion to heal her, but he has a coin which he can use to buy stuff. I added a Bitcoin for fun. There is a bandit, and the bandit wants to mug people, and the bandit has a sword which the bandit can use to slay people, and bandit is in his camp, and there's a coin in the bandit camp. So also there is another place which is a marketplace, and there's a guard in the marketplace who is trying to guard this marketplace, and there is and the guard has a sword which he can use to protect the marketplace, and in the marketplace there is a merchant, and merchant sells sword and also potion, which the Tom can use to heal his grandmother. And all these places are connected by a crossroad. In order to travel from one place to another, agents have to pass through these crossroads, and there's no direct connections between these places. So in this story, Tom wants to get potion somehow and take it back to his cottage so he can heal his grandmother. This story seems small and simple. You think that this story has a very small story graph too, but since the agents in this story can behave any way according to their beliefs, like if Tom thinks that the bandit is in the if Tom thinks that the merchant is in the bandit camp, he can move to bandit camp and get the potion from him from there. So there's a lot of things that each of these characters can do. So this story has a story graph with millions of nodes and states, and searching through that story graph to find a solution or a plan is very hard. So here's a plan that we solved using Sabre by searching that algorithm, searching that story graph with millions of nodes or states. Here, initially Tom is in his cottage, and Tom walks to the crossroads, and Tom walks to the market, and then Tom buys potion from the merchant. Tom buys potion from the merchant who is so Tom buys potion, and then Tom walks back to crossroads, and finally Tom walks back to his home or cottage, which is a terminal state, and this is an example for a plan. We also can get a story or a plan where Tom fails to buy potion, which is also an acceptable plan where the author goal is achieved. Here in this plan, first Tom walks to the crossroads, and bandit also walks to the crossroads, and bandit slays Tom. So these plans can be found using conventional searching algorithms like breadth first search. But the question is, can we find faster ways to do this search? Since these are directed graphs, since these directed graphs are not conventional directed graphs. So our motivation is to guide or modify existing algorithms like breadth first search so that
The plan. Who is doing the planning? Is it planning on the part of Tom, or is it planning on the part of the storyteller?
you can you can solve the problem for even for Bandit and any of the characters, but here we are solving the plan for Tom and also that which achieves author goals. Like author has a goal where if like Tom needs to get the potion back to his grandmother, so that's the author goal. And
So I'm confused. Tom plans to get killed by a bandit?
no, no, it achieves the author goal.
Ah,
So our motivation is to guide or modify existing algorithms like breadth first search, so that Sabre or any forward state searching algorithm can search faster. So in a conventional searching algorithm will take available state by random and expand that node to find a solution. So suppose that first event, the story that the algorithm will expand is that the Tom walks to crossroads, and then the algorithm will again select an available state or a node that and try to expand that. So after that, again the algorithm will select one from available state and expand that, and the process will repeat. But a human storyteller, once selected the first action, we'll see that after taking that action, there is a set of new actions that are available now that were not possible before taking that action. For example, here the Tom walks to the market action was not available before taking that action. Taking the action, Tom walks to the crossroads. So a human storyteller would, looking at this problem, would probably choose a second action that builds on the last action as the next step. Otherwise, what is the point of taking the previous action? But a planner, however, does not have such intuition, and it would consider any of the available second actions as an equally good choice. So our idea is to modify search algorithms so that they kind of behave how a human storyteller would. So that brings us to the topic of causally necessary actions. So what are these causally necessary actions? So let me give you an example of if Tom and Bandit are at their initial places. To Bandit's place Tom action to occur at the crossroads. Bandit needs to be at the crossroads, and also Tom needs to be at the crossroads. So what I'm saying is, in order to Bandit to slay Tom at crossroads, both need to be at the same place. Both need to be in the crossroads. So simply, in order to Bandit to slay Tom at the crossroads, both characters must walk to the crossroads. So our hypothesis is that action sequences which contain more causally necessary actions are more likely to be solutions to narrative planning problems than the sequences with fewer causally necessary actions. So that brings us to how we find causal necessity actions. So if we take the previous plan and leave the action bandit walks to crossroads and try to take the action directly from state 2 where the Tom walks to crossroads and the bandit Hassan walks to the crossroads, the plan does not make any sense. The plan does not make any sense anymore because the Tom is at the crossroads and the bandit is at his camp and he's trying to slay Tom, which does not make any sense. So we can understand that the bandit walks to the crossroads action is necessary to the plan. Hence, that action is causally necessary action, necessary to that plan. So let's look into an example of a causally unnecessary action. To do, I'm going to use this action sequence. So here, if we leave the action where Tom buys portion from the merchant and try to take the action Tom walks to the crossroads directly from state 2, that action sequence is still valid, which means that the action Tom buys portion from the merchant is not causally necessary to that action sequence. So to see how we applied that idea of causal necessity actions, let's go back to the previous story graph that I showed you and take these set of actions separately and reward the plans that has causally necessary actions by giving each action a cost, where if the previous action is causally necessary, we give some value that is less than 1, and if an action is not causally necessary, to that set of actions we give a cost of 1. So here you can see on the second sequence, the Tom walks to the market. In order Tom walks to a market happen, Tom needs to be at the crossroads, so it costs less than 1 on the second sequence. So then we calculate the total cost of that action sequence, and then when the algorithm expanding the state, instead of randomly choosing a plan, we can make the algorithm to choose the action sequence with the least total cost, which simulates what a human storyteller would do. So how we calculate the cost mathematically? Let's look into our algorithm. So we define total cost of an action sequence as a sum of causal necessity cost of each action, and let's call the total cost as cost of pi, where pi means the sequence of actions. So if an action is causally necessary, we give an epsilon value which is between 0 and 1, and we iterate over all the actions and leave the ith element and check if the action sequence is still valid. And for the last action, if the utility has been increased, we give that action an epsilon value, and if not, we give a value of 1. So let's say look into an example how total cost being calculated. I'm going to use 0.4 as the epsilon value in this example because we found that 0.4 works well as the epsilon value for most of our benchmarks. So let's start with the initial state, and the first action is Tom walking to the crossroads. Cost of that action is 1, and total cost of the plan is currently 1. And the second action is Tom walks to the market, and in order to Tom to walk to the market, Tom needs to be at the crossroads. So the action Tom walks to the crossroads become causally necessary. Hence, Tom walks to the crossroads action is now discounted. So it will get the cost of 0.4, and now the total cost is 1.4. So the next action is Tom buys portion from the merchant. Here, in order to Tom to buy portion, Tom needs to be at the market. Hence, Tom walks to market now causally necessary, and it will discount it, and now the total cost is 1.8. The next action is Tom walks back to the crossroads, and the total cost is now 2.8 because the Tom buys a portion from the merchant is not causally necessary for Tom walks back to the walk back to the crossroads. Now, when we get to the final action, something interesting happens. Tom walks to the crossroads is now obviously causally necessary, but the interesting thing is that total cost has been decreased from 2.8 to 2.6, since taking the last action increase their utility. So that is how we calculate the total cost of an action sequence. Also here the third action. Oh, I'm sorry. So in the third action is pretty special because it shows limitation of our approach, which I will talk in a minute. In a perfect world, this should cost 0.4 as well, or the value of epsilon. Now let's look into the modified search algorithms that we used. To make the search faster, so the first search method is uniform cost search. Here, the uniform cost search always extends the plan pi which has the lowest cost of the plan. And we used a modified A star search as well. Here, A star always extend the plan which has the lowest cost plus the heuristic, and heuristic is the estimates the number of actions remaining before the plan is a solution. And explanation first search, and in explanation first search, among all the plans, pi which contain only explained actions, it extends the plan with lowest cost plus heuristic. So let's move into results. So out of those 14 benchmark problems that I showed you earlier, we left out 4 problems: bribery, Aladdin, basketball, because and treasure problems, because they are either too small or too large to give a meaningful result. And we found that the standard deviations for the number of nodes visited and time spent during search were low enough, 10 runs that we did, to suggest that the values reported are representative for these problems. Also, discounting causally necessary actions usually improves performance, and it is important to mention that that when we do uniform cause search on the hunter problem with epsilon value of 0.4, the search visits 1,809 nodes, which is 9,076 fewer nodes than the baseline. And some problems which could not be solved using the baseline method can now be solved by discounting necessary actions. And we observed some negative results as well. Discounting causally necessary actions were not helpful for grandma, jailbreak, and lovers problems in any search method. So we succeeded on 7 domains, but we did not succeed on 3. Also, different values of epsilon often influenced uniform cause search, but generally, epsilon generally had a small effect on A star and explanation for search. So I'm showing a few interesting results that we got. Here, y-axis is the number of nodes visited. So fewer the better. And in uniform cause search, you can see that for space problem, fewer epsilon values worked better, and for radars, 0.4 value worked the best. Here is A star. So an A star did work better than UCS, and out of these 3 search algorithms, explanation for search works well, and lower values of epsilon are good for explanation for search for these problems. So as I told you earlier, our method have a limitation. Our method have limitations as well. So there are some causally unnecessary actions in these plans that are narratively necessary, but our method identify them. So let me go back to the example plan, and here the third action is necessary for the story, but does not get discounted because it is not causally necessary to the plan. In a perfect world, this action should also need to get discounted, but our approach cannot identify those kind of actions. So as a conclusion, we hypothesize that discounting causally necessary actions will allow a forward state space narrative planner to find solutions faster. However, the best search technique and the best discounting factor, and whether the large or small discounts were better, are varied by the problem. As future work, we would like to gather more benchmark problems and these tests with higher limit on the number of nodes visited to demonstrate a greater generalization. Also, that is important to mention that this method could easily implemented and efficiently calculated in a variety of domain-independent forward planners. So, thank you. Do you have any questions?
questions?
Thanks for your presentation. So I have two questions actually. The first question is in the example you showed, I don't remember the number of the slides, where you show the graph with the cost. Yeah, here. The question is how do you define the cost of each action here? For example, here you have 0.4 and 1. How this cost is defined?
Are you asking whether how I use the cost of 0.4 or like why few of them are 0.4 and some of them are 1?
I mean, how the number, how the cost is calculated for each of the different actions?
The total cost?
No, each cost in the area.
Okay. First, after taking the first action, let's go to the second action. So, in order to Tom to walk to market, first he need to be at the crossroads, right? Because so here, I'm sorry, not that one. So here, in order to Tom to go to the market, he first need to go to the crossroad, right? So here in in order to Tom walks to the market action happen, Tom first need to be at the crossroads. So this action is causally necessary to this action. In order to this action to happen, this action must happen before that. So that is why this become causally necessary to this action. So if that is the case, we give that action a cost of 0.4. But here, if we look at these two actions, in order to Tom to walk back to crossroads, Tom does not need to buy portion. So in order to this action to happen, this action is not causally necessary to this action. So we will give the cost 1 here. So in order for this plan to happen, we can leave this action and this plan still be valid. So Tom can walk to the crossroads. Tom can walk after Tom walk into the crossroads. Tom can walk to the market, and Tom can walk to the crossroads after Tom walks to the market, and Tom can go back to the home after Tom walk into the crossroads. So we can leave out this action and still this plan will be valid. So we give that action cost of 1. All the causally necessary actions we give cost of 0.4.
Yeah, that's correct. But why, for example, here you define the cost as 0.4, not 0.5?
Yeah.
I wanted to know how do you quantify value of the cost of one action?
We tested them like from 0 to 1.
Okay.
And when we found out that when there are a lot of like steps in a plan, lower cost work better, and like if there are small number of steps, the higher number of higher costs, higher epsilon values work better.
Is the optimal value?
Yeah, like we found out that 0.4 works better for most of the benchmark problems that we worked on.
Yeah, and also here, like you have the same action. Tom walks to the crossroads. and it actually appears twice in this
Yeah.
graph, right? So I'm wondering, like, perhaps the same action in different steps, it should have also different value here, the cost, because of maybe the current situation is different, and the same action you will take for the next steps, it might has a different cost. Is that the case, or you always have the same cost for the same action, regardless of in which state you are?
I get what you're saying, but I don't think it's easy to find how to like from states, like I don't know how to explain it, but here we can't give different epsilon value to all of those different like same actions, because it won't, I don't think it will make any difference like by doing that for what we are trying to do.
Okay. Okay, yeah. And
So what we are trying to do here is we are trying to differentiate what causally necessary actions and what are causally unnecessary actions. So by giving that a different value, it won't make any difference, but it's something we should like.
yeah,
look
just
into.
from my intuition, I feel like if you are in different states,
Mhm.
because of the different steps you take previously, it might impact the decision of your next step, right? Even with the same action, it might have a different value or different cost to take that action. This is what
yeah.
I understand.
You're saying like if we take the same action, we should, when we take the same action again, we should like think.
Maybe
yeah.
it.
Yeah.
I'm not sure because I don't work in this problem, but it's just
Yeah,
a
that's something we
question,
should look in. Yeah.
yeah,
Yeah.
came
Thank
in my mind. And also here, you just show like one action. Actually, you are showing the decision you are making in the sequence, right? Like how the action space is defined. Is it predefined or is like something you are calculating based on your current state?
I'm sorry, can you repeat?
I mean the action space
Yeah.
for each state. For example, here in the initial state, and then the Tom walks to the crossroad. Is the only action you can take?
Oh no,
Yeah,
there
there
are
should be
many
a bunch
actions.
of actions, right? And this action space is predefined, or it's something like the
It
application can handle to calculate this action space.
Like, are you asking whether how big is the issue?
No, I'm asking, like here, for example, now in the initial state, and you are showing the decision, the actions you take, the application choose is Tom walks to the crossroad. But
Yeah.
I suspect apart from this action, there should be a bunch of other
Yeah,
possible
yeah.
actions,
This is a
right?
plan that we like.
Yeah. So how this action space is calculated? It's like predefined or it's like automatically generated by the application?
The whole graph is generated by Sabre. The generated first. The story graph is generated using the Sabre, and then we search through that like this. So this is generated by Sabre, and then we to find a plan where from the initial state to the terminal state. So this is a, I'm not showing all the branches. This is a very big branched tree.
Okay, so the application, the Sabre, and can handle to generate this action space, right?
Sorry?
The application you are showing, the Sabre,
Yeah.
it can handle to calculate the action space.
Yeah, yeah.
Okay, okay. Thank you very much.
Yeah.
Any other questions? See, I have a couple of questions. First of all, I don't understand why Sabre, why is that action, particular action, chosen between the initial state and you call it state one? Or
Yeah.
you say that there are many, there are many actions that you can choose. So why is Sabre choosing that particular action? Any reason?
We are not choosing the action. We are choosing. I'm sorry. So here, you're asking why the planet.
You say that there are many possible choices for
Yeah.
between initial state and, like in this case, state two.
Yeah.
Then why is Tom Watts to the Crossroads chosen?
It's. I mean, like it chooses all those, all those available actions, and checks whether we are trying to find a plan out of those we are trying to choose the. Yeah, we are trying to find a plan or a path from the initial state to the terminal state. We are not choosing just one action. We are trying to find the whole path out of the graph.
And when you choose an action or a set of actions, one concern, of course, is to try to avoid the infinite loop. How do you avoid the infinite loop?
So it's the infinity loop is we can stop it by using if we look into the depth first search, we can limit how deep it goes, and how many actions it can take. So yes.
Sorry, this one's an implementation detail of this is an implementation detail of Sabre sort of, but also this particular design of narrative planning in general. The way that a valid action sequence is defined prevents any loops from happening, because if there's a loop, then it's not considered a valid action sequence. It's only a valid action sequence if there are no loops in it. And this is what prevents infinite loops from being considered.
So that's why the graph that Sabre gives you is a finite graph.
Yeah.
Because Sabre is avoiding even creating those loops.
Yeah.
Any other questions? We have plenty of time, so.
Is the objective to find the path which has the minimum cost from the initial state to the termination state?
No, we are trying to speed up the search by using this method. If you think about a normal graph, like a mathematical graph, we can try breadth first search and depth first search, but here these are specialized graphs. So the actions, all the actions that have been taken are the characters need to behave according to their beliefs and stuff. So what we're trying to do is we try to speed up and speed up the process of building the plan. like that's what we are trying to do. It's not what we are trying to do like the one with the lowest cost, of try to find the lowest cost.
Yeah. Initially, I was thinking about, the similarity between finding the minimum spanning tree within a graph, but I think you are doing more than that.
Yeah.
Right?
Saber will find the smallest path, but what we are trying to do is the finding that path, we speed up that process. Finding the path, we're trying to speed up that process.
I see.
When you say smallest path, is a path with the smallest cost or shortest path?
Smallest number of actions. How many actions that it can take? It will take. Yeah.
Smaller number of
Yeah.
actions.
So maybe just say smallest number of actions will not be that accurate. Like actually, Tom can just don't buy the portion from the merchant.
Oh yeah.
So maybe more well defined is I have several goals. Like I need to buy something, get to home.
Yeah.
With that condition satisfied, then we try to find a minimum path to achieve the goal. So with like a restricted minimum path problem, instead of just to say, I try to speed up a search process, rather we try to define the problem is what's the end product will be. We can say it's restricted. Restricted is I have several conditions need to meet. Otherwise, I don't have this condition. I can skip this, buy something from merchant step. Or if we don't define as a minimum path problem, then I can let Tom walk to the crossroad, then walk back to the market, then walk back to the crossroad, then walk home. Add the 2 extra steps, then I still see this is the problem. So maybe that's my try to explain what you try to achieve.
Yeah. Our goal is to get the portion back to grandmother, Tom. So the plan, the goal should be achieved, and it will give the smallest path which achieves that goal.
Any other questions? All right, we thank the speaker very much for
Thank you.